Okay. Can you start, Asha? Yeah.
Hi. Yeah, sure.
Okay.
Thank you.
I can hear you.
Yeah, thank you for the introduction. As the title says, this talk is about the tight security bounds for OMAC, XCBC, and TMAC. So I'll first give you a quick introduction of MACs and their security, and then define CBCMACs, basically XCBC, TMAC, and OMAC. Then I'll give you a discussion about the existing security results. And finally, I'll build up the main proof approach leading to the main results of the paper. So message authentication codes, or MACs, are symmetric key algorithms. So in this, we have two parties, Alice and Bob. They first agree on a shared secret key. And then suppose Alice wants to send a message to Bob with the added condition that Bob can authenticate that message is from Alice. So what Alice can do is she can take her key and the message and compute a authentication tag, a short tag, and then send this message and tag pair to Bob. Now Bob has the secret key, so he can recompute the tag and check if the received tag matches with this or not. If it does, then he accepts the message. If it does not, then he just rejects it. So this is the usual protocol for MAC. And what security means, so for security, we have another party called Eve, who is sitting between Alice and Bob and listening to all the communications. And Eve's goal is to forge Alice's identity. So basically, Eve will listen to all the communication from Alice to Bob and do some homework at her end, and then prepare a forged message and tag pair. So the condition is that this message and tag pair should be fresh. So that was a passive adversary where Eve was not actually choosing her messages. In standard proofs, we generally have a more stronger setting where Eve can receive the tag outputs on her choice of messages. But in both cases, she finally produces a forged but fresh message and tag pair. And then we say that Eve wins if Bob accepts the message finally. Interesting thing is, so MAC security is defined as this, the probability of forgery. And the interesting thing is that if Alice has a pure perfect random function, then the best Eve can do is to guess. So she can just guess the tag output for a fresh message. And often what we do is for the security of MAC construction, we quantify it via its ability to mimic a perfect random function. And this is done via a game called the pseudo-random function security. Here we have the ideal world where Alice has a perfect random function, and the real world where Alice has a keyed function. And the goal for Eve is to distinguish between the two worlds. So as usual, Eve interacts with Alice, but now instead of a message tag pair, she just returns a bit B at the end of the game. And then the goal for then the advantage of Eve is defined as this absolute difference of the probability that Eve returns 1 in the two worlds. A popular way of constructing MACs or PRFs is the CBCMAC, which is also one of the earliest PRF construction. In this construction, you first have a message M that we parse into blocks of n bits, where n is the block size of the underlying block cipher. So the important thing is that the mesh's length must be a multiple of n. So once we have this parsed message, you start encrypting the blocks iteratively. So first we encrypt the first message block, then we XOR the second message block and encrypt, and so on. And we do it for all the blocks, and finally we get the tag output. So as you can see, CBCMAC encryption is very simple. However, it has two major issues. First, it is susceptible to length extension attacks. So given that you have the CBCMAC for message M, you can compute CBCMAC for message M concatenated with any other string. And this gives you a forgery. And the second and more of a issue from the implementation point of view is that the input length must be a non-zero multiple of n. So to in a way rectify these two issues, several variants of CBCMAC were proposed, and I will concentrate on three constructions: OMAC, XCBC, and TMAC. And in all three constructions, as a pre-processing step, what you do is you take a message m prime, which is of arbitrary length, and you pad it to make a message m of length a multiple of n. So this padding is very simple, that if m prime is already a message of length multiple of n, then you simply put m equals m prime. Otherwise, you append a 1 followed by a minimum number of zeros to make the updated length a multiple of n. Once we have done this pre-processing, in XCBC, we first take the first L-1 blocks, apply CBCMAC, and then in the output, we XOR the last block, and we XOR a key depending on the type of message. So if the message length is a multiple of n, then we XOR K0, otherwise we XOR K1. So in a way, B differentiates between the two different types of messages that we can see. And finally, the updated state is encrypted again to get the tag output. TMAC does the same thing, but now it uses a constant element from the field instead of two different auxiliary keys. And the entire process is exactly similar. OMAC is even better in that it completely eliminates the key and adds to a constant as before. And here I would like to note that CMAC, a standard ISO standard and NIST recommended MAC algorithm, is just a variant of OMAC. So whatever I say about OMAC is also applicable to CMAC. And because OMAC is the best in terms of the number of keys, I'll mainly concentrate on OMAC in this talk. So now that I've given you an introduction about OMAC, let me give you a quick tour of the PRF security of OMAC. So the best bound till now is this expression that we have here. And it roughly says that Eve needs roughly square root of 2 to the n over L queries to either distinguish or forge OMAC. But the interesting thing is that there is no matching attack that achieves this bound. And in fact, all the folklore attacks are actually of collision finding nature, and they need roughly square root of 2 to the n queries. So the main bottleneck in getting an improved bound is the so-called full collision event. So let me describe it for you. So suppose the adversary made Q queries, 1 to Q, and we are concentrating on the ith query. So in the ith query, the tag value T is uniform at random. It's so we are in the ideal world right now. So the tag value T is uniform at random. And now in the ideal world, we want to mimic the real world computation. So we sample some E1 and we compute the OMAC. So because this tag value was already fixed, there is no guarantee that these two will match. These two will satisfy the permutation compatibility. So, and this is what causes this full collision event as well. So suppose you have a condition like this where there is another query J for which the final input of the ith query matches with an intermediate input of the jth query. So here xj2 collides with xil. But now, because Ti is completely independent of this processing, it might be possible that Ti is not, with high probability, it will be the case that Ti is not equal to Yj2. So, which is the issue? So, in more generally, what we have is we have two different queries I and J, and a block A such that Xj is equal to Xil, and this is an issue that has to be handled. And there's a very simple way to handle it is we have two different queries. So Q choose 2 times the number of blocks, which is L. So it's roughly Q square L. And then each such collision results in a 1 over 2 to the n probability. So this probability can be easily bounded by this order. And this is the main bottleneck in the security bound as well. So if we want to improve over this bound, then this particular event has to be handled differently. And actually at Asiacrypt last year, we presented a new proof approach called reset sampling that solved a similar issue for LightMAC as well. And actually in the same paper, we also hinted that this technique might be useful for OMAC as well. And how we do this? So suppose we have this event. So instead of this full collision event, what we bound or what we disallow is this compound event, where the subsequent input here xj3 is also colliding with some other input. So although a bit tedious to handle, this actually gives us another n-bit entropy. And in the paper, we have shown that this can be easily bounded to this expression, and which is straight away better than the existing bound. So now that we disallow those events, we can go back to the full collision event. And for this, we simply reset this yj2 with ti. So because there is a equality on the inputs, we just make the outputs equal. And as soon as we change the output, it changes the next input. And what can happen is that this next input might collide with something else. And if this kind of collision happens, this is a bit trickier to handle as compared to LightMAC. So in LightMAC also, we had the same issues, but it was easy to handle there. Whereas in this case, we have to do something extra. So let's discuss this issue in detail. So first, the simple case. Suppose this collision happens at in the kth query at somewhere in the middle, except for so more importantly, not at the first block. Then it can be handled as before, and because you have 2 equalities and 3 queries and 2 blocks, you get a bound like this. But if it happens at the first block, and additionally, suppose the kth query occurs after the ith and jth query, then adversary can easily fix this first block by this relation. So you can make mk1 equal ti xor mj3, which in a way like makes this second equality a consequence of the first equality. So as soon as the first equality holds, this second equality holds trivially. And this is an issue. So what I'm trying to hint at is that we need another round of resetting, something that we call induced resetting in the paper. So how induced resetting work? So I have added 2 more blocks here just to describe the induced resetting. So obviously the inputs are colliding here. So what we have to do is we have to reset the next output. So the resetting is happening on the jth query, and the kth query is basically providing the values for resetting. So we have to reset the next output. Now, ordinarily it should be enough, but now what can happen is mk2 might be equal to mj4, right? So the next block, next message block might be equal. So in that case, the next input is also equal. And that means we have to again reset. And in this way, we have to keep on going until the 2 message blocks differ. So in this case, mk3 and mj5 are different. So xk3 and xj5 are different. So here we can stop. But as soon as you stop, you have to again perform another sanity check whether xj5 matches something or not. So this is again like a second level of sanity check. So first we checked something like this, and now there is another check where xj5 might equal something else. But the good news is that this can be bounded easily, and after handling this tricky case and some case-by-case analysis, we can actually get our main result, which is this expression. And if you translate it into into a statement, then basically it says that Eve needs minimum of square root of 2 to the n and 2 to the n over L squared queries. So it's not exactly the minimum, but if you attack, you generally attack via one of the two techniques. So that's why it's a minimum of square root of 2 to the n and 2 to the n over L squared queries. And if you want to compare with the existing bounds or the folklore bound, then it's clear that while we do not quite achieve the folklore bound, it is still a step towards a tighter bound. So for instance, if we take n equals 128 and consider a graph of number of queries q versus the maximum message length L, there's a clear daylight between the folklore and the existing bounds. But if we now put our bound here, it is very close to the folklore bound. In fact, up to the message lengths of almost 64 gigabytes. It's very close to the folklore bound, and it performs better than the existing bounds up to 64 terabytes. So it's almost like messages generally are much smaller than a gigabyte. So the bound in general is quite good. So in conclusion, what we have shown is that OMAC is almost birthday bound secure. And like in the full paper, we have shown similar results for XCBC and TMAC as well. So I will conclude with some future directions of research. So first and obvious direction is, of course, the new application of reset sampling, particularly towards the beyond birthday bound single keyed constructions, how to improve their security. And the second direction is to explore the possibility of improving the bounds in this paper. So our bounds, the L value, for example, here it's L squared in the denominator. So how we can improve it further so that the relaxation on the message length can be, the restriction on the message length can be relaxed. And finally, our approach towards reset sampling is quite ad hoc, to be honest, for now, both in case of LightMac and in case of OMAC. So what would be interesting is to see an abstract formalization of this tool so that it might be easier to apply to other constructions as well. So with this, I will end my talk. Thank you for your attention.
Okay, thank you for speakers. Any questions or comments? Can you check online question? No? No question. Okay, it seems there's no question.
Yeah.
Okay, thanks speakers again.
Thank you.
Okay, next talk is it's online, in person. So a modular approach to the circuit analysis of two permutation construction by Yudong Chen.
Okay, thank you for the introduction. Okay, so yeah, as the title says, this paper is about permutation-based constructions. So that's due to the announcements of SHA-3 hash function competition in 2007, which makes Keccak as a winner in 2012. And then since Keccak is a permutation-based hash function, which makes permutation, yeah, it leads to popularization of permutation-based constructions. So indeed, not only for hash functions, there are different types of constructions based on permutations. For example, here we have a block cipher. Yeah, it's a triple block cipher. And this is a PIF that we introduced in Crypto 2019. And here's another type of PIF. And we also have a MAC algorithm based on public permutations. And this is also something that's called a TCCR hash function. which we introduced in Asiacrypt last year, and that's most suitable for the MPC applications. You may not be familiar with all those constructions, but you can see that actually all those constructions are based on two permutation calls. The reason, therefore, is that's actually the minimum number of primitive iteration needed to achieve beyond birthday bound security when lightweight application is considered. So maybe it's good to first go to the security notion of permutation-based constructions. So in order to do that, we first need to define an attack game. So at the beginning of the game, one of those two worlds is chosen, either the real world on the left side or the ideal world on the right side. So then this attacker here should, it's given query access to one of those two worlds, and it should state which of the two worlds it was interacting with at the end of the game. So the attacker A can make Q queries to the construction oracle. It's either on the left side, it's the proposed construction, or the idealized version of the proposed construction on the ideal side. Besides construction oracle, besides the construction query, the attacker can also make P primitive query to each of the primitive oracle pi1 to pi r. Those are actually the primitive where the construction in the real world is built on. Well, it is independent of the ideal world's construction oracle. Now, the security in this case is measured by the probability that the attacker can distinguish the two worlds. So it's denoted by this advantage function, which is actually a function of P and Q. The more queries that you can ask, the higher the probability that the attacker can distinguish the two systems. Then the given construction is only secure if this advantage function is negligible. However, that's only the case when a single user is considered. When we move to a more practical situation where there are multiple users, each using an independent key, then the situation is a little bit different because the attacker makes Q queries to U construction oracles. In the real world, that represents U users using the same construction, each with an independent key, while in the ideal world, those are just independently drawn random oracle, ideal version of the construction. The case for the primitive queries are still the same. However, this time the attacker succeeds as long as it can compromise one of the user key. Now, in this case, we can actually obtain the multi-user security from the single user security by simply multiply it with a factor U. But when this U, the number of users, is very large, then the security bond becomes very impractical. Then, okay. So in order to solve this problem, maybe it's good to look at how the security proofs are performed in the symmetric key world, I would say. So one of the most used methods to prove the security of symmetric key constructions is Badra's EdgeCoefficient technique, which is stated here. I'm not going to explain it into detail, but the idea behind is just a small set of transcript that appears with very high probability than the other transcript. And then the advantage of the adversary is actually bounded by those two terms, this blue epsilon and this green probability. There are three steps that need to be performed. Then the first one is, of course, define those bad transcripts that appears with very high probability. And the second one is we want to bound this probability of those bad transcripts in the ideal world. And the last one is this epsilon term, which is related to the good transcripts that are the transcripts that's excluding the bad ones. That's in the real world, and the ratio of the good transcripts in the real world with that's in the ideal world. Now we can see that actually by the definition, the first and the last steps actually totally depend on how the construction is designed. Well, the second step is actually a purely combinatorial problem and only depends on the randomness of the key. That means the more key that you use in the construction, the easier to perform this analysis. Now, the question arises whether it's possible to have a modular approach for the first and the last step, since that this is totally different problem than the second step. In order to give yeah, if we have a modular approach, then yeah, I would say that's much easier, that we don't need to perform dedicated proof every time a new construction is designed. In order to do that, yeah, we first need to look at this problem here where yeah, we consider two sets of unknowns U and V and Y. And then we also consider system of bivariate equations and norm equations, where those V, Y, and V dots and Y dots are unknown values, and those lambda and lambda dots are actually the known values. Then there are two index mapping that we can define that maps the unknowns in the system to those two sets of unknowns. Then one of the way to then the goal here is actually to determine a lower bound on the number of solutions to those systems. Then one of the solution is actually Paterna's mirror theory, which is also talked about. Yeah, it's also discussed during a talk in this morning. Then there we need to represent a system of equations and non-equations by a graph. So here so each distinct unknown is represented by a vertex with the unknown value, while each equation is represented by a lambda labeled edge, and a known equation is by a lambda dot labeled edge. Now, the thing is that there are some properties that the transcript should satisfy. For example, it shouldn't contain a circle. If this case happens, then it actually says the distance between those two nodes is equal to lambda 1, while at the same time it's equal to lambda 2. That is actually very inconsistent. And the second one is that it shouldn't contain any zero path label, because according to this, the distance between those two nodes are lambda, which is also equal to the distance between those two nodes, while those two nodes are not the same. The last property is related to the norm equations. It says that shouldn't be any circle with lambda dot labeled edge, such that the value of lambda dots is equal to the sum of all those lambda values. Look at this example here. So this component actually says that distance between those two nodes is equal to lambda. Well, the distance between those two nodes cannot be lambda dots, because that's a norm equation. Once this lambda dot is equal to lambda, then of course the components, that's inconsistency. So those are actually the properties that needed to define the bad transcripts in the security analysis. However, the problem is Paterna's mirror theory is actually for block cipher-based PRF constructions. So if we want to use it through the permutation-based setting and we want to extend it to different type of notions, we need to go a little bit farther. So in this work, we'll focus mainly on all constructions that can be fields like this, where the value A, B, and E it's actually the functions of secret key input and the output. Now, as said before, the security analysis is performed in the ideal permutation model, and therefore the attacker has query access to the underlying primitive pi1 and pi2, which are modeled as random. Now, that means we should also take the primitive queries in this form into account. If we try to add those primitive queries into the system, then we can see that the system of equations is extended by 2 P univariate equations. That means that the index mapping is also different. However, because the fact that we know all those lambda values, then those additional I would say P unknowns V and this P equations on Y. So there, the unknown V and Y are well defined. That means a part of the sets of unknown V and Y is also defined. Now, if we move on this those system of equations and known equations to the transcript graph, so those are the things that's needed for the general setting. And here we need to add a primitive query. Then it is represented by a known vertex with known value, which we will denote by a white vertex. And then there's also extra components that need to be introduced. That's called colliding components. That means a component that contains a vertex with no value. For those type of components, all vertex, the value of all vertex are well defined. It's very easy to see because let's say here we have those components by ignoring all component with path length of 3 or higher, then we can see that those are actually the colliding components. If we know the value of the white vertex, and we know the value of the labels in the edge, those are the lambda values, then we can perfectly define those black nodes. So, okay. So, however, there are some properties that the graph should satisfy in order to apply the theory. For example, there cannot be any component with more than one colliding or one white vertex. The reason is very simple, because we know exactly the value of this node. We also know exactly the value of this node, and we also know the value of the edge label. So there's no guarantee that the XOR between those two nodes is equal to this lambda value in this edge. Then the second property that it should satisfy is that there cannot be, I would say, norm equations that's connecting two colliding components such that the distance between the two connected vertex is equal to this lambda dot. The reason is also very simple, because as mentioned before, we know exactly all the values of all those nodes in a colliding component. Then suppose the two connected vertices, their value is equal to A and B, then the fact that they are connected with the norm equation means that they should satisfy the property A XOR B is not equal to lambda. However, if the fact that we know exactly the value of A and B and lambda dot, then suppose lambda dot is equal to A XOR B, then of course that's inconsistency. So take all those properties into account, we can derive or extend the traditional mirror theory in the permutation-based setting, and we can apply those to different type of constructions with different security notions. And maybe first to explain a single framework to use those, to use a technique given a construction that can be filled like this. And we have a query transcripts in the following form, including the primitive queries, and the keys are given at the end of the interaction. Then we can represent the query transcript by this system of equations and norm equations. And using those systems, we can define the batch transcripts. Then when we have the batch transcript, we can easily use the new theory to obtain this epsilon value. Now, some examples. So we applied to 3 different constructions to obtain the user security of those constructions. The first one is actually the Trico block cipher Trico Ifamasu by Gosniadi et al. In 2015. So they show the single user security is 2n/3. However, here we can show the multi-user security by, for example, replacing this pi2 by pi2 inverse in order to apply the theory that can be done, since we are working in the ideal permutation model, and the permutations are assumed to be perfectly random. And then this is A and this is B. Well, this middle value is actually it's equal to H1 XOR H2. Then we can show with our model approach that it have 2n/3 bit security in the multi-user setting, which is comparable to the single user case. The second example is actually the PRF permutation-based EDM proposed by Duda et al. In 2021, where they also showed 2n/3 bits single user security. Then we use the same trick as before, and then that this part is A and this is B, and the middle part is actually K2 XOR with feed forward. So the security analysis of in the multi-user setting is actually more complex than the single user setting, since in the single user case, the input to pi1 is always fresh, since this M should always be fresh. But for when multiple users are considered, there's no guarantee that the input to pi1 across multiple users are still fresh. So the analysis is a bit more complex, but we can still obtain 2n/3 bit security in the multi-user setting using our modular security technique, which is also comparable to a single user case. And the last one is actually the MAC algorithm, which is a permutation-based NEHTM construction proposed by Duda et al. In 2020, where they show that it has 2n/3 bit security in the single user setting. However, using our approach, we can see there's actually a flaw in the security analysis. Since the authors miss some bad events, those are actually the bad events that they are missing. I represent this by the form of the components that they should have been excluded. I'm not going to talk in detail about those components. You can find the details in the paper. But then the consequence is that due to the fact that those events are missing, the good transcript analysis is also incomplete. And therefore, in this work, also with my other work with the authors, we find two different ways to solve this problem. So the left-hand side, you see the way that I have with the authors in my other paper, where we just make a very simple modification by XORing the key on the right-hand side. However, this leads to a much more difficult security proof. Well, in this work, since we only focus on modular approach, I just simply add more randomness at the end. And then we can apply our technique in order to solve it in a very simple way. And then this A, this B, and this part is the middle part, and we can show the construction indeed achieve 2n/3 bits multi-user security, and as claimed by the author for the single user setting. So so those are the application on the new technique. So here comes the end of my presentation. The new result of this work is a model proof technique for permutation-based constructions based on traditional mirror theory, and we present a framework to use this new technique. And we apply this new technique to prove the multi-user security of 3 constructions. And then some future research directions for the one is maybe we can design the deterministic MAC and AEs based on public permutations using our new technique. And there's also a way maybe find a model approach for the multi-user security proof for the permutation-based constructions, and generalize the model proof technique for more difficult constructions. So that's the end, and thank you for your attention.
Okay, thank you. Any question, please? I have a question anyway. So your approach seems very easy to analyze by combining modular functions together.
Yeah.
But you are assumed that multi-user case, multi-user can use this together. But in crypto scenario, the multi-user are always honest or dishonest, So we need some assumption. User are all equal privilege to join this function, or any other dishonest users, if they join, what happened anyway? So you assume that all users are honest, right?
And so the definition here is just that the attacker, it has access to all those user and oracles. So it can query to all those user oracles. That's actually the assumption of the multi-user security in this work. So the attacker have access to all those oracles, but then the oracles use either independent keys in the real world or is randomly drawn in the ideal world. So there's so the assumption that the randomness in the oracle is still, I would say, totally independent from each other.
So you should assume that the attacker is outside the attacker. You do not assume that inside the attacker, inside the hacker something.
You mean that?
So any part of multi-user behave very honestly, you can assume. Otherwise, what happened?
I think that's indeed a very it is a little bit different assumption than that's used in this work here. I think therefore that's probably something that's need to be discussed.
Okay.
It seems the security notion in this work is just assuming that the attack have the black box access to all those oracles, and then with independent keys. So your assumption is probably a little bit yeah, different than here. So
Oh, yeah.
I'm not sure how it can behave. That's yeah.
Okay. So any other questions? No? Online? Can you? Okay, one more question over there.
Hi, Yulong?
Yes.
Yeah,
I think there's still someone else who want to ask a question or yeah.
Yeah, I would like to ask one question about the bound for NEHTM. Can you go to that slide? I think the previous slide or yeah. So here you have this for the multi-user. You have this you choose 2 over 2 to the n bound.
Yeah.
Can you describe like how this is like achieved or why this is coming up?
Yeah, and that appears in one of the bad events that I analyzed. So therefore, so I think that's that's collision in the keys or something, but I cannot remember all the details. But it appears that there is such bond. But when there's
yes,
yeah.
sorry, yeah, you please complete.
So in the case when single user security is considered, then yeah, this bond becomes 0, right? Because if you it's u times u minus 1, then if u is equal to 1, then this bond disappears. So
yeah. So yeah. I was thinking that because here you have 2 different keys, 3 different keys, the key k, the hash function h, and then h star. So
yeah,
shouldn't the bound be better than this? Like even for multi-user,
you mean,
because now it's saying that there's a birthday bound. So do you have a attack that captures this bound or?
Wait,
because the key size is bigger now. Key size is not just n bit, right?
Yes,
so,
but the reason that I use this H star is because otherwise, yeah, much more difficult techniques needed to bond the bad event. But I don't think this is really can be really called the birthday bond security, since the number of users is usually to assume to not be more than the total number of queries that can be made here. And the total number of queries here can be made is still this, yeah, the Q term, and it's still 2n over 3. Indeed, there's yeah, birthday bond security in the relation with the number of users. That is correct. But I think if I remember that correctly, because yeah, it's a little bit a long time ago, that the last bond comes from some bad event that I'm bonding. I'm not saying that this bond, this term is necessary, since probably if you use some more involved technique or something, maybe there's a way to have a better bonds in the bad transcripts and avoid the last term. That's something that's yeah, that I cannot guarantee. So, but it's just using yeah, just using simple yeah, without using special technique, I obtain this U bond in the security analysis.
Oh, okay. Thank you. Thank you for the answer. Thank you.
Okay.
Okay, thank you for your presentation. I think it's more advantageous some interpretation of security analysis in terms of more intuitive. Is there some button for generating some kind of graph form of the these equations compared to traditional security analysis techniques?
So let me understand your question clearly. So you mean, is there any relations between the generalization of those equations with traditional techniques? And yeah, actually, so in the traditional techniques, you actually, yeah, so you actually perform more or less the same thing, but you don't really set those things into the system of equations and its known equations. But apparently, if you if you move to a system of equations and norm equations, then there can be, I would say that there can be a more, better relationship with the good transcript analysis and and the mere theory here. And then the thing is that once we can represent this this system by, or the transcript by a graph, then using some simple technique or some definitions in the graph theory, we can obtain a much better bond. I'm not sure if that's will be the case for much more involved constructions, but for the constructions that can be filled in this way, then that's definitely the case. So maybe it's for future research to consider difficult constructions.
Okay, let's thank speaker again. Thank you. Next talk is, you can leave it there. Okay, thank you. Optimizing rectangular attacks, a unified and a generic framework for key recovery, authored by Ling Song, Nana Zhang, Kuan-Xiang Yang, Dangxin Xu, Jiajia Xiao, Liu Hui, Jian Huang, and Nana Chang will give a talk. Nana, is it ready?
Yes. Can you see the screen?
Just
Okay.
wait.
Thanks for
Just
the
wait.
introduction.
Okay, we are ready. Nana,
Okay.
you can start now.
Okay, thanks for the introduction. Hello, everyone. My name is Nana Zhang. In this talk, I will introduce our paper, Optimizing Rectangle Attacks, a unified and generic framework for key recovery. And I will introduce the paper from the following 5 parts. First, I will start with some preliminary knowledge. Boomerang attack is a differential style attack to construct a long differential utilizing 2 short ones of high probability. As shown in the figure, in boomerang attack, we encrypt a pair of plain texts P1, P2 with a difference alpha to corresponding pair of ciphertexts C1, C2, and each ciphertext is XORed with difference delta. Then, the modified ciphertexts C3, C4 are decrypted to a new plaintext pair, P3, P4. If the difference of the new pair is exactly alpha, the quartet P1, P2, P3, P4 is a right quartet. Rectangle attack is a chosen plaintext variant of boomerang. And in this work, we mainly focus on mounting rectangle key recovery attacks as efficiently as possible. Next, I'm going to introduce the outline and some specific parameters for rectangle key recovery attacks. This figure shows the outline of rectangle key recovery attack. The notions in the figure are borrowed from previous works on the rectangle attacks, which are used frequently. Here, we highlight some new parameters used in our paper. KB prime refers to part of KB to be guessed in this work, and MB prime refers to the number of sub-K bits of KB prime. RB prime denotes the condition can be verified under the guess of KB prime for plain text. In EB, when we guess all the MB sub-K bits, we can verify the total RB bits conditions for a plain text pair. Then, if we guess the partial MB prime sub-K bits, the corresponding RB prime bits conditions will be verified. And we further denote MB star and RB star as the rest of the involved sub-K and filtering conditions in EB respectively. The above definitions can be applied to bottom EF completely, and we don't make redundant descriptions. Before specifying our work, we provide some new insights into the rectangle key recovery attacks. The key recovery of rectangle attacks always include steps of constructing pairs from single messages and constructing quartets from pairs. And the whole key recovery can always be split into 4 steps: data collection, quartet, pair construction, quartet constructing and processing, and exhaustive search. Following these procedures, 4 rectangle key recovery algorithms have been presented using 4 kinds of different subkey guessing strategies in previous works. We investigate these rectangle key recovery algorithms in depth and observed that these algorithms differ mainly in strategy of guessing subkeys and the ways of constructing quartets. Actually, we can construct pairs either in plain text side or in cipher text side. Then, the first question came into our minds is whether there are any other ways to mount a rectangle key recovery attack. The answer is yes. From the point of view of subkey guessing, there are 5 new types of key recovery key guessing strategies. Key guessing strategies. In previous works, the 4 algorithms were treated as separated ones, and their performances vary from case to case. But in this paper, we attempt to mount rectangle key recovery attacks in a unified way. First of all, we consider a generic way of guessing subkey KB prime and KF prime, which is part of KB and KF respectively. Then it comes to question 2. How does the key recovery algorithm proceed when KB prime and KF prime are guessed? Taking the ways of guessing subkeys and the ways of constructing quartets together, we present a generic and unified algorithm which supports any possible attacking parameters. And I will now introduce our generic and unified algorithm, which is the most important work in our paper. In data collection phase, collect and store Y structures of 2 to the power RB plain texts each. Then we guess part of the subkey bits involved in key recovery part, and we will obtain RB prime bit and RF prime bit filtering conditions in EB and EF respectively. Totally, we can get N minus RB star minus mu bit filtering conditions in EB and N minus RF star filters in EF. Note that the number of filtering conditions are also related to the number of the structure or the data. Using these conditions, we construct pairs. When we construct pairs, we can filter the wrong pairs in advance. As we can acquire filters in both plain text side and the cipher text side, we can construct pairs from either plain text side or cipher text side, and the filtering condition in another side will be used in generating quartets. Then we need to decide which side to start with to reduce the time complexity of constructing pairs and quartets. We expect to filter the wrong pairs as many as possible at the beginning. With this in mind, we compare the number of filtering conditions in plain text side with the number in the cipher text side to decide the way of quartet construction If there are more filters in the plain text set, we construct pairs in the plain text set using the filtering conditions by constructing set S with hash tables in which the pairs have difference only in RB star bits. Then we generate quartets from the remaining pairs in set S, and the number of quartets we will obtain can be calculated from the following expression. If there are more filters in the ciphertext set, we construct pairs from the ciphertexts and generate quartets in the other side, which is similar with the former case. After constructing quartets, we need to determine the K candidates in EB and EF with the remaining quartets. Finally, we guess the remaining unknown K bits according to the K schedule and recover the correct key by exhaustive search. According to our detailed algorithm, we can compute the data, memory, and time complexity of the algorithm. And from the united algorithm, it is clear that any possible guessing strategy should be allowed, and that there must be a guessing strategy leading to the optimal complexity of the key recovery attack. Then there comes a question: what is the best choice for KB prime, KF prime, so that the overall time complexity is minimized? To answer this question, we present a framework to automatically finding the best attacking parameters and the minimal time complexities as a complement. The automatic framework takes related parameters on our Boomerang or rectangle distinguisher and extended key recovery rounds as input, and returns KB prime, KF prime, and the minimal time complexity. In essence, this is an optimization problem. When it comes to a specific cipher, one can instantiate it and solve it with MILP solvers or set solvers. Our framework is modular, and we describe it as a template. The first module is difference propagation. We model the differentials and compute RB and RF. Then we need to value pass, mark the state cells whose value are needed, and compute the sub-K involved in EB and EF in guess and determine. Model the relation between the sub-K bits and the internal state cells. That is to say, model the filters. Considering K bridging, we model the relation between sub-K bits according to the K schedule algorithm and compute the number of independent guessed sub-K bits. Last, we compute the time complexity and set the objective function to minimize the overall time complexity. Combining the algorithm and the framework, we are able to find the most efficient rectangle key recovery attack. Our new algorithm unifies all the previous rectangle key recovery algorithms. That is to say, any of the previous 4 algorithms is a special case of our algorithm. By replacing the corresponding parameters, the exact number of guessed sub-K bits, and the number of resulted filters in our formula of complexity, our algorithm can be converted into corresponding special cases. Given a rectangle distinguisher, one can compute the complexities for different algorithms and pick the one with the lowest complexity. But with our algorithm, we can work with this one only. The best parameters to minimize the time complexity may lie outside the 4 previous cases, and we find that the best attacking parameters differ significantly from these which were used in previous works, including the setting for MB prime and MF prime, the set of constructing pairs, and even the number of rounds added around the distinguisher. It is likely that previous rectangle attacks can be improved to some extent using our new key recovery algorithm. And then to demonstrate the efficiency of our new key recovery algorithm, we apply it to 4-block ciphers using existing distinguishers. We give better attacks on 10-round serpent, improve some of the best attacks for skinning in previous works, extend the rectangle attack on craft by 1 round, and give the first 19-round attack. And we improve the 11-round rectangle attack and extend the boomerang attack by 1 round in the related tricky setting for deoxys. Our results are summarized in the table, and the results of this work are highlighted in the table. In addition to the aforementioned works, we developed several variants of the new key recovery algorithm for related attacks. For case RB equals N, we change the way of choosing plain text, and our algorithm can easily adapt it to the related key setting for ciphers with a linear key schedule. Considering boomerang attack, we specially propose variants of the key recovery for the case extending rounds in only one set. In conclusion, in our work, we propose a unified and generic rectangle key recovery algorithm. It can support any number of guessed key bits, covering 4 previous algorithms and unveiling 5 types of new algorithms. As a complement, we present a framework for automatically finding the best parameters for the new algorithm. Besides, we apply it to 4-block ciphers using existing distinguishers and obtain a series of improved results. That's all. Thank you for listening.
Thank you, Nana. Any question, please? Okay, over there. So can you hand it microphone over there?
Thank you for your presentation. I have one question. By any chance, this framework, can this framework be applied to key recovery of retracing boomerang attack proposed at Eurocrypt 2020? Because in the case of retracing boomerang attack, there is a specific filtering process. So I just wonder.
Sorry, can you repeat it?
The question here is, can you apply your assault to the Eurocrypt 2022 paper to key recovery attack?
Retracing boomerang attack. Can this framework be applied to retracing boomerang attack?
To what?
Retracing boomerang attack.
Iterated boomerang attack, something like that. Right?
Retracing.
Retracing boomerang attack. You have never heard about that?
A
Nana?
retracing formula.
Yes.
Thanks for your question. We are not all, we are doing this work, and but this work was not included in this paper.
Okay.
Okay, thank you.
Any other? Nana, can I ask a question?
Okay.
So your method improved previous 4 algorithm, right? Your idea improved 4 previous algorithm 1, 2, 3, 4,
Yes.
right?
Yes.
In your presentation, you mentioned that if previous attack can be improved, combining your attack some extent. So which algorithm mostly improved by using your method? 1, 2, 3, 4. Can you hear me, Nana?
Sorry.
Okay, it seems difficult to understand anyway. So if there's no question, let me conclude this session. Okay, thanks
okay.
speakers and thanks speakers and questions. Thank you. We can take a break.
Okay, thank you.